So the title of my talk in your program is The Possible Futures of Pacific Northwest Ecosystems, which is what happens when your boss writes your abstract and doesn't give you a chance to look at the final version. I don't think we have quite enough time for that, given the geologic timescales upon which that might be based. So I shortened it down to possible futures of Pacific Northwest ecosystems, but then I realized really 20 minutes, so this is kind of going to be a possible future of Pacific Northwest ecosystems. And this is based on work I've done along with Dominique Bachelet and Ken Ferschweiler, whom I work with at the Conservation Biology Institute. And we use data from John Abatzoglu's group at the University of Idaho. He did the downscale data that we used. So I'm going to cover some of the scope and methods of this study, a very brief look at climate, and then jump into the modeling results, looking at some fire, vegetation, and carbon, and then temper the findings with some takeaway messages. So the study area, oddly enough, corresponds with the name of the conference. It's the Northwestern United States. It comprises Oregon, Washington, Idaho, and parts of Montana. And we divided our domain into 3 study regions. We did grouping based on EPA Level 3 ecoregions, using climate and or elevation similarities between areas. The first of these areas is the west-northwest, which is the crest of the Cascades west, basically. The second is the Northwest Plains and Plateau, as we call it. These are the flatter and lower lying areas to the east of the Cascades, and then the east-northwest mountains, the mountainous regions west of the Cascades. These just kind of fell out in their similarities, as I said. So the approach we took, we used the MC2 DGVM, which has biochemistry, biogeography, and fire modules. And the fire, I want to take a couple of seconds to mention a few things, full disclosure. We assume ignitions using fuel condition thresholds. So basically, if fuel conditions get fire prone enough, get dry enough, we assume that there is an ignition that will lead to a burn. Obviously, it's a big simplification of reality. And we run it with and without fire suppression. So with fire suppression, we set those thresholds lower. So we end up with more frequent fires and less severe fires. With fire suppression, we set those thresholds higher. So fires tend to be less frequent, but they are more severe. And we implement fire suppression starting in the year 1950 to reflect the real history. The model in this run, or in these runs, we modeled potential vegetation. This is the vegetation that we feel would be growing on the ground without consideration for the history or land use. And then we also implemented limited CO2 effects, so water use efficiency with CO2. The inputs we used for the models came from 20 climate futures, from the CMIP5 RCP 8.5 scenario. It's the business as usual scenario. And for the DGVM results that we'll be looking at today, we looked at the carbon budget, we looked at fire occurrence and effects, and we looked at vegetation dynamics. So climate, I said it was going to be short, and here it is. It's going to be warmer. All the projections agree on this. This is the ensemble mean of temperature change from the late 20th century to the 21st century, and you can see it ranges from about 4 degrees centigrade to 6.6 degrees centigrade, and it's generally more warming as you move east. Precipitation, there's less agreement between models. In general, there's a little less summer precipitation, but the 20 models that went into these ensemble results did have a bit of variation in there. So let's look at fire, something I find exciting. And you know, if it's close enough, I bet you would too. This is a map of mean fire interval, and we call it mean fire interval. It's basically the fire return interval. We term it mean fire interval because fire return interval often implies you're looking at things over a longer scale of time. Here we're looking at the 20th century and the 21st century, 100 years. So something with a 500-year fire return interval wouldn't show up so much on these. As you can see, fire is more frequent in the future, and fire is less frequent with fire suppression. So the historic at the top with fire suppression directly below that, and without fire suppression to the right. You can see there's more yellow on the map with the as you go down that progression. So some things to note, that in the 20th century, fire was pretty much absent from the west-northwest region and the higher elevations east of the Cascades. With fire, even with fire suppression, we get fire in those regions, and without fire suppression, we get more frequent fire. So we've got some areas that are going from, in our model, no fire whatsoever to 1 or 2 burns or more over a century. Fire suppression shows up as being very effective in some areas. The areas circled here show that, and you might say, wait a minute, how come fire suppression is working better in the 21st century than in the 20th century? And that goes back to the fact that we only did it over half of the 20th century. So these results have those unfire suppressed years in them for the historical. And the final thing, I think it's the final thing I'm going to point out about fire, is that there's little fire along the coast and in the Olympics, even into the future. We looked at the fire rotation period in addition to the mean fire interval. I'm not showing the results here because 20 minutes. The fire rotation period shows similar effects as the mean fire interval. It's shorter in the future, and it's somewhat longer with fire suppression than without. So, following up on fire, I want to look at vegetation type instability. What the heck is it? So the MC2 has approximately 36 different vegetation types that we're using in it. And we built a table for a weighted difference between each pair of vegetation types. And the differences are based on the climate they're in, the phenology, and the density of wood. And so we came up with a 0 to 5 index for each of these pairs. And just for an example, if we started out with a subalpine forest and we went to a temperate needle-leaf forest, those are different, but they're not that different, so that gets a 1. If we went from that to a temperate warm mixed forest, we're getting further away from our starting point. That would get a 3. And if it turned into a subtropical mixed forest, that would be quite a change, and that would get a 5. And we measure this in different ways, or we calculate it in different ways. Sometimes we do it over the yearly average. So what's the yearly change? And we average that over the whole time period. We look at a maximum 1-year change. So over the whole time period, what's the biggest change it experienced in 1 year? And we also look at the maximum over time. We take all pairs every year versus every other year. what's the maximum range that happened over the time period. So the maximum 1 year change, it usually reflects a disturbance. If you're going to move away quickly, it takes something big to do it normally. And really? I'm 5 in or 5?
Oh, so you have another 10 minutes for the whole time.
Okay. All right, I'm going to start talking faster. It reflects disturbance. It's high in areas with introduced fire. Maximum change over time takes into account succession and shifting potential vegetation also, and it's greater in the future. The aggravated vegetation classes, we just looked at subalpine, conifer, mixed shrubland and grassland. The big takeaways here are in the west-northwest, we see this huge shift from conifer to mixed. And in higher elevation regions, we have a big shift from subalpine to other conifer. And the other thing is we also get shrubland expanding at the expense of grasslands. And that effect is with fire suppression, but not so much without. Forested area, the light green shows increases in forested area. It's most common along the edges of current forested area, and if you squint real hard, you might be able to see the orangish brown from the brown. My apologies on the color map there. You get a little more shift from forest to non-forest without fire suppression. Carbon, this is kind of what I'm excited about on this study so far. You see we have a lot of gains and losses. You get losses in some areas with greater fire. That's to be expected. It burns up. And this is this is live forest carbon, so this is trees. But you also get gains in live forest carbon density even in areas that experience more fire. And as you might expect, you get gains where there's increased forest. And the results are similar with and without fire suppression. If you look at total carbon, you see a similar pattern, but fire suppression has more an effect, as you can see if you use your imagination on part of this and if you don't on the other. In the Columbia Plateau, for instance, you're getting more carbon with fire suppression than without, and you're losing a little more on the west-northwest. So the quantities reflected here turned out to be, I thought, really interesting. The west-northwest drives the overall loss in forest carbon, so that's live forest carbon. You can see it doesn't change too much in the other regions. And the fire suppression has a limited effect here. It's adding about 500 teragrams for the full northwest. But the change in total carbon adds about 1,300 with fire suppression. So what does it mean? So I'm trying to make sense of the projections. Here's where I wave my arms and tell you what I think. Warming temperatures lead to more fire-conducive events. You also get a tendency towards some drier summers and more variability in precipitation. In addition, you get increased production leading to increased fuel. For the vegetation shifts, loss of subalpine, things get warmer, you're not subalpine anymore, it's not that hard. Shift to the mixed forest in the west-northwest, that is a huge thing that we're modeling. It's warmer, drier summers, and it's not solely driven by fire. This is why I outlined the coast earlier, because we get this shift even along the coast where we don't get more fire. For expanding forests, this is kind of an interesting thing. We get increased productivity versus increased fire. It sounds like a cheap superhero movie. Maybe that's a future for me. The CO2 effect increases water use efficiency. We get a longer growing season, but increased fire consumes forests. Except in the west-northwest, the increased productivity generally wins out when it comes to forest carbon. Or when it comes to forests. And again, with carbon, increased productivity versus increased fire. But what about that fire suppression effect on total carbon? That was a big deal. It turns out if you prevent the small fires, it allows a greater buildup in dead carbon pools. That's the fuel that builds up that leads to the bigger fires under fire suppression. But there's some implications that need to be thought about here, especially when you think about managing for the future. We want fireproof forests. We want to sequester a lot of carbon. You might have to choose. If you treat the fuels, if you do controlled burns, you're going to reduce the sequestered carbon according to what we're showing here. So just a word on limitations to try to answer a lot of questions that you all want to ask. Did you think about land use? Yes, we think about land use. We have one version of the code with land use in it. It needs work. We're working on it. Invasive species. Yes, we know it's a disturbance. I'm meeting with someone this afternoon to talk more about that. Well, invasive species, no, that's pests I'm talking with this afternoon. Invasive species, you may get openings where invasive species can come in, cheatgrass or something like that. It changes the whole thing. I'm not promising to do much with that. And assumed ignitions, fire is complicated. Yes, we know fire is complicated. I am actively working on improving the fire model here. So, using these results, what?
I say that all the time too.
Yeah, it's true. The question is the model I'm using useful or not? Because I know it's wrong. The results need to go into context. How does it match up with observations? What do experts in the field say? Both modeling experts, experts in ecology, any expert who will talk to you. We produce models that produce results that need interpretation, and that interpretation should lead to improvement in the models. Another thing, we're not the only game in town, as you saw from the first talk. There are other models out there, there are other data sets, there are other studies. Pick the one or ones that are appropriate for your scale and purpose. And above all, these results represent one possible future, not all of them. So I'd like to acknowledge the Northwest Climate Science Center for funding, the World Climate Research Program's Working Group on Coupled Modeling for CMIP-5, R. Namani at NASA, who gave us access to the supercomputers that we use to run this, and John Abatzoglu and Catherine Hegowich at the University of Idaho for a lot of time and a lot of work on downscaling the data we used and working through problems we had along the way. And now I don't know how much time I have for questions. If I'm lucky, not a whole lot.
One question.
One question, okay. One question, not the zombie apocalypse question.
Could you tell me a little more about how you modeled fire suppression? Like, are you assuming a certain success level in repressing fires, and you expect that to remain the same at the end of the century as fuels accumulate if you are suppressing fire?
The logic we used was that if a fire burns, there's a point where if a fire burns this intensely, you can't put it out. And so we set our thresholds. We have one threshold that says we could have a fire here, and if we could have a fire, we assume an ignition. With fire suppression, we say if our conditions are this severe, then an ignition could not be put out, and off it goes. And part of the work I'm doing currently is to bring in some probabilistic factors to that to most likely get a wider variety of burns.
And when you include fire suppression in the model, does that interact with the model to create more fuels as well, so leading to more severe fires?
Well, it doesn't say create more fuels. It just says don't burn the fuels that are there until conditions get this severe. Am I clear enough?
Yeah.
The look on your face says no. But I have that problem with a lot of people. All right, thank you very much.